Hello and good morning, everybody, and welcome to the CEIA Maths Tutorials online again. Today we have probability with Edmund Collins, who you've met already.
Good morning, everybody, and welcome to this tutorial on probability. It's good to be with you again this morning. I met you at some of the previous tutorials on indices, logs, and trigonometry. Now, I must admit that this mightn't be my favorite topic. However, I did enjoy putting together this tutorial because I learned a bit more maybe about probability than I had known, and it's certainly a very interesting topic and comes up quite a bit in physics, finance, and other areas, as you'll see now in a minute. So we'll get started. So the applications, so they are varied, particularly let's say around actuaries in working in insurance. They have to determine the probability of accidents occurring, storms occurring, and so on, in order to set premiums. So it would come up quite a bit in that area. So if you look at the photo here on the top right hand side, that some of you may recognize that's the International Space Station, and it's a screenshot of some assessment that was done in relation to the International Space Station being hit by space debris. But they would have again used probability tools to determine high areas of risk. So there's a lot of debris now out in space, satellites breaking up and so on. So the space station could be exposed to a hit. So that's where probability was used in that area. Last but not least, here at the bottom of the screen, in quantum mechanics, quantum physics, it's used extensively. So it's a very interesting area, and also used in thermodynamics and entropy and so on. Probability is a big subject there, and if any of you go on to study physics, you're definitely going to come across probability in that course. So very interesting area. Studied it a little, and certainly saw where probability came into its own there. So the scope of this morning's tutorial will start with some fundamental principles of counting, starting with the multiplication principle and then going on to the addition principle. Now, as you know from previous tutorials, it's very important that you understand the tools of the trade, so to speak, and principle of counting is very much part of the whole probability problem solving toolkit. So we'll start off with those principles, moving on to permutations, then on to combinations, and we'll have a quick look at Pascal's triangle and binomial coefficients. So that'll probably be the first part of the tutorial, take about an hour. We're going to take a break for about 10 minutes, and then we'll move on to probability proper itself. But really, the second part of the tutorial is going to be built on the first part. So it's important that we understand what's going on with principles of counting and so on. In the second part, then we'll start with probability concepts. Set theory is a very important part of probability problem solving. The axioms of probability, probability of success and failure, the rules of probability, the general addition rule, and also the general multiplication rule. We will be doing along the way one or two problems from Leaving Cert papers. Now, just in relation to problem solving and questions on probability in the Leaving Cert, it's interesting that the questions often don't require a lot of working in that sense that, you know, you would in a trigonometry question, whatever, you'd have quite a bit of working out to do, calculations and so on, using algebra and that type of thing. The probability questions don't tend to have a lot of that, but you really need to think and quite hard about the solution to the question. So there's more thought around it rather than the hard work. But you'll see that as we go along, that is the case. Certainly the example that we have from one of the Leaving Cert papers 2019, there is a bit of working in that one, but not a whole lot. Really, it's around the understanding of the problem. So it's very important when you're doing a question on probability to really read the question very, very carefully, underline things and so on. And hopefully by the end of the tutorial, you'll have seen that approach. I must give credit to Aidan Rowntree's Effective Maths 2 for help in putting together the slides here, and I've used some of the material, some questions from Aidan's book in this tutorial. So I want to acknowledge that reference book. They're very good maths books, Maths 1 and 2, and I've used them for these tutorials over the last number of years. But certainly without Aidan's book, it mightn't have been as easy to put together this tutorial. So I just want to mention that. So we'll start in on the principles of counting. So the first principle we're going to look at is the multiplication principle. So I set up quite a simple example here, but it does show the principle quite well, I think. So a restaurant has a menu here, which consists of a starter, a mains, and a dessert. So it's quite a simple restaurant. They don't offer too much, but in relation to the starter, the options are option 1 is soup, and option 2 is salad. There's no option 3 or option 4. So in terms of the terminology, we're going to say that there are 2 outcomes for the starter, or two options, if you like. Then for the main course, you can have a meat dish, fish dish, a vegetarian dish. So therefore, there are three outcomes or 3 options. Now they're quite good on desserts in this restaurant, and on this menu, you have 4 options. So you can have ice cream, fruit, meringue, and tiramisu. So they're the 4 outcomes there. So the meals, however, when you go into this restaurant, the condition of dining there is that the meal must include 1 starter and 1 mains and 1 dessert. So it's very important. I've put in the and here in bold. Then the total, according to the multiplication principle, the total possible meal outcomes are 2 multiplied by 3 multiplied by 4, which equals 24. So they're the total possible outcomes. But you'll notice that the and translates into multiplication here. So that's why it's called the multiplication principle. So that's the first principle that we'll look at. Here's an example, a bit more complicated, but it shows how the multiplication principle could be used in a security code, for example. So the security code is to be comprised of 2 uppercase letters and 2 digits. Very important now in this case, we're talking about upper or lowercase, but when we're dealing with options, in this example, it's only uppercase. So if there was upper and lowercase, we'd double the options, but only uppercase here. So how many code options are possible? So using the same approach that we took before. So for character 1, it can be any uppercase letter. So that's 26. For character 2, which is an alpha character, another letter. Again, it can be 26. For character 3, that's a number from 0 to 9. So that gives us 10 options, and include the 0. And then for character 4, it's the same again, 0 to 9, so 10 options. So the codes can be made up of 26 letters and one of 26 letters and one of 10 digits and one of 10 digits. So again, using the multiplication principle, we just multiply out all the different options here, 26 by 26 by 10 by 10. And actually we come out with a very large number, 67,600 different options for the code combinations for two alpha, two numeric. So you can imagine as we go on to greater numbers, that the options are very, very large. So it's just an interesting example of the application of the multiplication principle in a security code. Now, the second fundamental principle of counting is called the addition principle. So we're back to our same restaurant again, with the 2 starters, 3 mains, and 4 desserts. But in this case, the restaurant gives the customer some more options in terms of the types of meals. So the first option is the three-course meal that we saw before, comprised of 1 starter, 1 mains, and 1 dessert. But then there's an or you can have a 2-course meal comprised of 1 starter and 1 mains, or a 2-course meal comprised of 1 mains and 1 dessert. So what happens here, you notice that the or is going to be converted into plus here. But that there is the multiplication principle is built in here. So we see the multiplication principle being used here, but we also see now that we're introducing plus. So these are the or options. So the first option that we had seen before, 2 by 3 by 4. The second option, the 2 by 3. So two starter by 3 mains, the options there, and then finally we have 3 mains by 4 desserts here. So it's 24 plus 6 plus 12 equals 42. So they're the number of options, a lot more than we had with the multiplication principle. So having done some of the basic theory there, we'll move on to looking at sequences, permutations, and combinations. Now it can be a bit confusing when you're looking at these three different ways of presenting a set, if you like, of numbers. But you'll find that in leading set questions, combinations come in quite a bit more. Now, I'm not saying that you wouldn't have permutations coming in, potentially sequences, but combinations are most frequently seen in the questions that I've seen anyway. But it is important to understand the difference between the 3 of them. So this table, I hope, explains it. So in terms of the sequence here, so a sequence is a sequence or a permutation is an arrangement of elements where the order matters. So by order, we mean that 1, 2 is not the same as 2, 1. However, in a combination, order does not matter. So 1, 2 and 2, 1 are considered to be the same. Now, important difference as well between the sequence and permutation combination is that repetitions are allowed in the sequence. By repetitions, so if we have 3 elements, 1, 2, 3, well then 1, 1, and we want to make up two elements, set of 2 elements, then 1, 1 is allowed, but not in no repetition in permutation combination. So it's either 1, 2, 2, 1 or whatever, but not 1, 1, 2, 2, that type of thing. So this summarizes it here, what we've talked about. So in an arrangement, 1, 2, 3 is not the same as 3, 2, 1. We've talked about that. But in a selection, for example, so this would be a combination. An apple and orange is the same as an orange and an apple. So if you look at the logic around that, it's quite easy to understand. But if you're looking at a countdown sequence or something, 1, 2, 3 is not the same as 3, 2, 1. So hopefully that helps now in terms of the difference between the two. But as I say, combinations tend to come in a lot more than permutations or sequences. So here's an example of a permutation. So the definition of a permutation is an arrangement of objects in a particular order with no repetitions, and that's from the previous slide. So if we have a set here with just one digit in the set, one unique digit in the set, well then the only possible permutation is 1. So we summarize this 1 by 1, and you'll see here now, we'll come to this last column in a minute. But if we have 2 unique digits, 1 and 2, well then the permutations can be 1, 2 or 2, 1. You notice there's no 2, 2, 1, 1 or whatever in here because the repetition is not allowed. And also 1, 2 is different to 2, 1. So then we've 2 permutations here, and that's 2 by 1 here. So if we have 3 unique digits, the permutations are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So we've got 6. So this equates to 3 by 2 by 1, which in turn, you're probably familiar with this designation, the 3 exclamation mark here, that's 3 factorial 3. So basically what we're saying here, all this is leading up, is that if we have n unique digits, excuse me, the number of arrangements is factorial n. So n multiplied by n by -1, n by -2, and so on down to 1, where n is a natural number, and factorial 0 equals 1. Very important to remember that. You could be lulled into thinking that factorial 0 was equal to 0, but it is equal to 1. And there's some proofs available online if you want to look at them to see why factorial 0 equals 1, but it does. So that's an important part of the definition of a permutation. Now, permutations are often shown in this form here. Now I'm going to use this NPR, and later you'll see I'll be using NCR. But anyway, in this case, NPR, so you have to be familiar with it. So P is obviously indicating its permutation. N is the upper or superscript. The R is the subscript. So this is the definition of the series, if you like, that NPR equals n factorial n, sorry, divided by n factorial n minus r, which equates to what we've looked at already. That's n by n minus 1 and so on, where n is a natural number, factorial 0 is 1, and very importantly, that r is always less than or equal to n, or cannot be greater than n, but it can be equal to n. So if r equals n, so we have an NPN here, then we have factorial n divided by n factorial n minus n, which is equal to factorial n divided by factorial 0. And as we've just seen, factorial 0 is 1. So that equates to factorial n, which is back to the previous slide we would have looked at. So how can this be used? Well, in this example here, we're looking at 2-letter permutations. How many of these can be made from the letters A, B, C, D, and E? So n is the total number of elements, if you like, in the set. So we're talking about 5 here, but we want to select 2 out of the 5. So n equals 5 or equals 2, as we see here. So we can put that into our formula here. So we have factorial 5 here, divided by factorial 5 minus 3, which is factorial 3. So if you work that out here, it's 5 by 4 by 3 by 2 by 1, divided by 3 by 2 by 1. That's 120 divided by 6. That equals 20. Now, there are quicker ways of doing this, and we'll be looking at that now in a minute in terms of calculators and so on. But it is important that you understand the formulae and so on behind these, that you have an idea of what the result is going to be. So that's permutations. Now, moving on to combinations, quite similar in terms of how they're designated, superscript, subscript, and so on here. So n, again, same. C, indication it's a combination, and or here again. So the formula for NCR is factorial n divided by factorial r multiplied by factorial n minus r, and that equates to this here. Again, n is to be a natural number. Our friend here, factorial 0 equals 1, and r is less than or equal to n. So again, very important, or cannot be greater than n, but it can be equal to it. So again, if we plug in r being equal to n, then the series simplifies to this formula, factorial n divided by factorial n multiplied by factorial n minus n. Again, this all simplifies out to actually 1. So that's interesting there, that's for n equals to, or equals to n, it comes down to 1. So in this example here, if we want again to have a 2-letter combination, this time not a permutation combination, that can be made from the letters A, B, C, D, and E. So we plug an or into our formula here. So n is 5, or is 2. So we have factorial 5 divided by factorial 2 multiplied by factorial 3, and so on. So working all that out, that equals 120 divided by 12, which equals 10. Now, just going back to the previous slide, you'd see here that the permutation for the same 2 letters out of our 2 letter combinations from 5 letters was 20. In this case, it's 10. So this is a rule that you'll always have less combinations than permutations, and this is back to the order and so on. So because the order is not important in the combination. So always less combinations than permutations. So that's just something to remember. Now, just briefly looking at Pascal's triangle and binomial coefficients. This comes up a bit further into probability outside of the scope of this tutorial, but it is important to understand the triangle, and I think it's quite an interesting development by a very talented mathematician who did an awful lot of work on probability, but he developed this triangle. So I've just shown 8 rows here, because obviously we're talking about row 0 here to 7, so total 8. But it goes on to infinity and so on. You can keep going with it, but it has some very interesting properties here. So you'll see that there's 1 on the outside here, and then if we go down here and this line here, 1, 2, 3, 4, 5, 6, 7, and there's pattern here, 1, 3, 3 to 6, the difference is 3, 6 to 10, difference is 4, and so on 5. So there are some interesting aspects to it. And again, this going down, this line is the same as this line, and so on. This line here is the same as this line here. But basically what it's saying here is that this is a combination, an NCR type combination. Now, in some problems, you'll see this NCR written as in this way, brackets n on top or below. I prefer this designation here because it's clearer, I think, with the C, with the combination. But it is sometimes shown as this, so just to be familiar with that. Anyway, NCR is the binomial coefficient where n is the row number and r is the element number. Now remember, we have a row 0 as well, and we have an element 0 as well. But if we take the case of row 5, element 2, so we have row 5 here. This is element 0, element 1, element 2. So if we plug in the values for n and r, 5 and 2 in this case, then we get 10. So that's the value here. And the case of row 7, element 3. So that's element 0, 1, 2, 3, which is actually 4. So R is going to be 4 here. In this case, R was 3. So we plug in row 7, n equals 7, and R equals 4. We get 35. So this is a summary, if you like, of NCR for based on the triangle. So it comes up in other areas, but it is an interesting piece of work, and certainly it's got very interesting properties. So we now look at a summary here of what we've been talking about in relation to sequences, permutations, and combinations for a set numbers 1, 2, 3. So n is that set 1, 2, 3, and or is 2. So we want to pick two numbers out of this set of 1, 2, 3. So if we look at the sequence first here, so sequence is actually n to the power of r. That's how a sequence would be designated here in relation to n being 3 and r being 2. So that means we have actually 9 elements for sequence, as you see here. So the elements are 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. Now you can see here that duplicates are allowed here. So 2, 2 is allowed. 1, 3, 1 is different to 1, 3. So if we move on to permutation now, the NPR, so plugging in 3 for n and 2 for r here, we see 1, 1 isn't allowed. No repetitions. 1, 2 is allowed. 1, 3 is allowed. 2, 1 is allowed. 2, 3, 3, 1, and 3, 2 are allowed. So that they are 1, 3 is considered different to the 3, 1 in permutation. So in this case, we have 6 options here. And finally, then, with our combinations, the NCR, with n being 3 and r being 2, it's quite similar to the permutation in that 1, 1, 2, 1, 3 is allowed, but 2, 1 isn't allowed, because in a combination, 2, 1 is considered the same as 1, 2, so we can't count it twice. 2, 3 is allowed, but 3, 2 isn't allowed, or 3, 1, because that would be counting it again twice. So in this case, we've only 3 options. So it's an interesting summary here, because it does show that in the case of sequence, you have a lot more results than you would have in the case of permutation, than you would have in the case of a combination. But really, back to the point again, you're going to have always less combinations than permutations. Now, earlier on, I talked about the use of calculators when working with NPR and NCR. So it's very important that you're familiar with your calculator before going into the exam, that you check that it's an approved calculator for the exam, so you get some information on the exam website. It's a good resource, the exam website. You can also get past papers, solutions, and so on. This is my calculator, Casio calculator, scientific calculator, and it's, as you can see here, there's two options here, one for NPR and this option here for NCR. So how this is used is you key in n first. So if n was 3, whatever, you key that in, 3, then use the shift key here to bring up the function. So C will appear. And then if r, let's say, is 2, you key in 2 and then hit equal. So that's if you were working with a combination. If you're working with permutation, you do the same thing, n first, then whatever n is, 6, hit the key here, and you'll get a P coming up, and then you enter or, if it was 2, whatever, then you press equal. So very important to be familiar with that, because it'll save you a bit of work when you're doing NCR calculations. Certainly don't want to be going back to the formula for calculating it out. So calculator will be the way to go. I have looked at the tables, the formula, maths and formula tables, and there isn't a whole lot actually around the probability space in the version I have, but it's important to check them out as well, to make sure you know where the relevant formulae are. But there's, as I say, there doesn't seem to be a whole lot around probability. That's something to bear in mind. So we're going to have a quick look at this question, but we have a few poll questions during this tutorial, and before answering this question, we're going to bring up the poll now in a minute, but I'll just read it out first. So this was from a fairly recent paper, paper 2, 2019, question 1, part B. So as I mentioned earlier, it's very important to read these probability questions, well, any question, but particularly probability questions, very carefully, because ands and ors and options and so on are going to coming up. So and underline particular words, I would suggest. So the question is, an examination paper is made up of 2 sections. Section A consisting of 7 questions, and section B consisting of 8 questions. The paper contains the following instruction. From section A, you must answer 1 and any 3 other questions. So the first thing I'd say is the and there. So remember, and what we looked at in the earlier part of the presentation. From section B, you must also answer any 4 questions. So there's a number of ands here. So question 1 and 3 other questions from A, and from question B, 4 questions. So find how many different combinations. So again, very important combinations here, into combinations territory of questions that may be answered if a candidate follows the instructions. So Eamon, we might bring up the poll, please. Okay, so I'm going to give you a few minutes to think about this question, how you'd answer it. So the first question to consider is what principle of counting should be used to solve this question? I'll give you a hint there. So is it the addition principle or the multiplication principle? So second question in the poll, how many NCR calculations are required to be completed? So would we be doing 1 NCR calculation, 2 NCR calculations, or 3 NCR calculations? So hopefully if you've pen and paper, because we're going to need it a little bit later on as well, and 1 or 2 of the other questions, but you might just consider that, and we'll give you a few minutes before we'll close the poll. Okay, will we close the poll, so Eamon, and see what we've got? Interesting. Very good to see the response to the multiplication principle. Yeah, that's correct. However, not surprised actually to see that people have thought that there was only two NCR calculations. There are in fact three. But there could be, I suppose, in fairness, looking at the solution, you could do it in cut one step out, but really to do it correctly, there'd be three. Anyway, we'll have a look at the solution now. Thank you, Eamon. So I'm just going to do it on the screen rather than coming out into an app. So using this designation for NCR. So so from section 1, you must answer question 1. So actually, this is the first NCR calculation. So you have to answer one question out of one. Little tricky, but working through the steps, that is the case, and it's important to have that because, as you'll see then, and you're right, we're using the multiplication principle here. The second NCR calculation here is and why it's important to have done the first one here is that because section A is 7 questions, and you must answer number 1. You're left then with 6 questions. So the 3 other questions that you're going to answer are out of 6, not out of 7. And that's where you could end up in a bit of trouble answering this question. So in this case, N is 6 and R is 3. So excuse the writing there. And again, multiplication principle. So then finally, then the last part is easy enough. From section B, you must answer 4 questions. Section B is a total of 8. So 8 by 4. So that's it really, but tricky enough with this this question here. But if what might have happened is that you might have taken the 3 out of the 7 or whatever, so that could cause you to lose marks. So working out then what the NCRs are here. In the first case, it's just 1. In the second case, it's 20. If you want to practice using your calculator for that, you can. And in the last case, it's 70. So total of 1400. Quite a lot, really. A lot of options there. So the combinations, 1400. So hopefully that gives you an idea of the use of NCR and the counting theory and so on. So it was an easy enough question, as you can see. Very little working out really in it, but a lot of thinking to come up with the correct solution. Now we're doing quite well on time, so before we move into probability, we might just take the break now a little earlier, Eamon, if that's okay.
Sure, that's perfect. I've got one question coming in there on the Q&A.
Yes.
Why isn't the first combination 7C1?
Sorry, could you repeat that again, Eamon?
Why isn't the first combination, you've got 1, 1, 1. Why
Yeah.
isn't it 7C1? It's because you have to answer one question. You have to answer question 1, isn't it?
Yes. Yeah. Yeah. Question 1. You've no choice. It's 1 of 1. So that's it. It's not 1 out of 7 because you haven't got the option. You can't answer that number 1. You must answer question 1. You've no choice. It's 1 out of 1. So that's valid for an NCR. We saw that n can be equal to r. This is the example here. So it's 1 out of 1. But as I mentioned, going through it, once you've answered that one, then you bring down the number of options then, because the paper contains, or the part A contains 7. So you're 3 in the second case, second NCR. You're answering 3 out of the 6 questions because you've already answered number 1. If that's clear.
I think that makes sense anyway. There was another question just came in.
Yep.
How do you know it's the multiplication principle?
Well, the and really.
It's one question, 1 and
that, and we saw that, when we were doing the counting theory. If it was a case of or, you must do 1 out of part A or 2 out of part B. Well, then you would be looking at the addition principle. But they can be a combination. We're going to see in a more complex problem coming up that they can be combined. You can have both the multiplication and the addition principle used in solving a question. So that gets a bit more complex, but there is an example coming up shortly where we'll see that. Welcome back, everybody. So hopefully you've got something from the first part of the tutorial, and we'll build on what we covered in the first part now, in the second part, getting into probability in more detail. But you'll see combinations and so on are going to come into this part quite a bit. So the first thing is to look at the probability line, and it's quite straightforward, really. At the two ends of the line here, we have at 0 probability, it's impossible, never happen. And then at the other end, we're certain it's going to happen, an event's going to happen. So the probability of that is 1. So the scale of probability is 0 to 1, inclusive, so including 0 and 1. If you're working on a problem and you end up with a negative probability or a probability greater than 1, you've made a mistake. So that's something to bear in mind. So nicely in the middle there, you'll see the even chance. So this would be the case if you often hear this 50-50 chance. So that's the even chance. And often in probability, the example is given of a non-biased coin, whatever that is. But anyway, if you toss it an infinite number of times, 50 times you get heads, or 50% of the time you get heads, 50% of the time you get tails. So that's the even chance there. So just looking at the left-hand side there. Sorry, just getting my pointer here. So in the case of a die here, if you toss it, the chance of getting a 1 is 1 in 6, because the 6 numbers on the die. So that's the case here. in this case here, it's just showing some billiard balls maybe. So there's 5 balls, four are color blue, 1 red. So the chance of picking, let's say, a blue ball would be 4 and 5. So that's the probability line. Just quite simple really, but I think it's a nice demonstration of it. So some concepts here. So what's often talking about in probability is an experiment or a trial which has outcomes, and then the sample space is very important concept, and that's the set of all possible outcomes. And then you have an event E here. So S is used to designate the sample space, and the event is designated by E, uppercase E. This is something that may or may not occur when an experiment is conducted and is a subset of the sample space. So by definition then, the probability of an event E, so it's designated this way, P brackets E, is the number of times that E occurs over the total number of trials. And this just shows what we've looked at before on the probability line, that the probability of event must be greater or equal to 0, but less than or equal to 1. So that's important. So the probability of equally likely outcomes, and this is our designation back to our R and N here, is the number of favorable outcomes over the total number of possible outcomes. So it can be a bit difficult to relate back to our NCR here, but we need to do that really here. So N here being the total number of possible outcomes and the number of favorable outcomes. So, you know, what are we hoping to find or achieve? So a little different to what we've been looking at earlier, but you'll see now that the calculations, certainly for combinations, are the same as what we did in the first part of the tutorial. Now we're going to be having another poll in a minute or so now when we've read through this question, but I'd like you to start doing a bit of work on this before I go through the solution. So I'll be giving you some time to do that. But it's an interesting question taken again from Aidan Rountree's book, Effective Maths. So it relates to markers contained in a bag. So a bag contains 4 red, 3 blue, and 5 white markers. 3 markers are drawn at random from those in the bag. One person bets, Brian bets, that all 3 markers will be of different colors, while Katie bets that all 3 markers will be of the same color. So the question is, determine who has the greatest probability of winning the bet. So we might bring up the poll there, Eamon, please. So the first question I'm asking in the poll here is, what are the total number of possible outcomes in this situation? So is it 15? Is it 60? Or is it 220? And then what principle of counting that we looked at earlier should be used to solve this question? Is it the addition principle, the multiplication principle, or are we going to use both? So maybe you just look at that problem. Again, it's important to read through it carefully. Think about the different options and how the question is worded, and then consider what tools you're going to use to solve the question. So I'll give you a few minutes to consider that and enter your answers to the poll, and then we'll go on and look at the question. Really what we need to consider here is the number of, if we look at here, the number of markers in the bag are 4, 3, and 5. So there's 12 markers, and we're going to be picking three markers from the 12. So from that, then using the NCR here, N is 12, or is 3, and if you calculate that using a calculator, the NCR, you'll see that that's 220. So that's the total number of possible outcomes. So that's the sample space. So 220. You were all right here in terms of where we do use the multiplication and the addition principles both in this solution here. So the first thing, the first step here is to calculate the sample space. So we've done that using NCR. The second step then is to calculate probability of the event 1, where all 3 markers will be of different colors. So we are going to, if they're going to be different colors, it means that we're going to have to get one marker from the 4 red, and very important here, the and, one marker from the 3 blue, and one marker from the 5 white. So again, this indicates with the and, by writing it out here, that we're into multiplication principle territory here. So the probability of that event, the NCRs, we multiply each of the NCRs out. So for the first, we have N is 4 and the R is 1. In the second, we have N is 3 and R is 1. And in the third, we have N is 5 and R is 1. So working that out, we have 4 by 3 by 5, which is 60, using the multiplication principle. So then, in order to calculate the probability of that event, we just divide the probability of the event 60 by the number of possible outcomes, which we calculated here has been 220, and that can simplify down into that 60 over 220, or 3 over 11. So that's the probability of selecting three different colors. So in the next step here, we're looking at all 3 markers will be of the same color. So quite similar here, but we're just saying we're going to have 3 from the 4 red, or, it's important writing it out, or 3 from 3 blue, or 3 from the 5 white.
Sorry,
So,
Ed, sorry
yep.
to interrupt you there. Now I've got a question that just came in.
That's fine.
I think it's from the last section. Why doesn't 4 by 3 by 5 equals 60 work for the total number of possible outcomes? Well, sorry, the total number of, because
the total number of possible outcomes is the sample space here. This is the first step here is to calculate the total possible outcomes of all the combinations, if you like, from those different markers, and that's the sample space. That's the 220. Well, this step here, the 60, is the probability of that particular event occurring, not of the total sample space. So the total number of possible outcomes, i.e. the sample space, is this. It's 3 from these 12 markers. So I know it's a little tricky to get your head around, but that's the sample space. That's the total different combinations of the 4, 3, and 5 different colors. Okay. So in the second option, where we're getting the 3 from the 4 red, or the 3 from the 3 blue, or the 3 from the 5 white, we're using the addition principle here because it's the ORs here, as you can see, but we do use the NCR for each one of them. So the NCR here, N4 or 3, N3 or 3, and N5 or 3, which works out at 4 plus 1 plus 10, which equals 15. So again, it's 15 over the total sample space, the 220, which simplifies to 3 over 44. So therefore, the event 1, I think was it Brian, whoever, who said that there would be 3 markers from different colors. That is the greater probability of occurring. 3 over 11 as against 3 over 44. And I suppose if you think of it in the real world as well, the likelihood of taking out 3 markers all of the same color from your experience would be a lot less. If you were putting money on it, you'd certainly be saying that the chance of picking different colors would be higher than pulling 3 of the same. And this bears it out in this question. I know it's there's a bit in it, in terms of, first of all, calculating the sample space and then using the multiplication and the addition for the 2 different options. But again, with these, is the more questions you do, the better you get at understanding the principles. So the thing is to try different questions and build your understanding. Now we're going to move along to set theory, and set theory is very important in probability problem solving, and you need to be familiar with the concepts used in sets and the terminology. There's not that much in it really, and there are some good YouTube videos online for set theory, which, if you're a bit unsure of it, would be worthwhile looking at those. But we'll go through it here anyway. So basically what happens here is that the sample space normally is designated by this rectangle here, and we've seen it's called S here. The event here is the circle in the middle of the sample space here, and that's called E. So if we have 2 events, so in this case A and B, in a sample space. So if we want to determine, let's say, the probability of both of them occurring, so that would be A intersection B. So that's how that's designated. So inverted U. So that's the space where an event where both A and B occur. However, and that's colored red here at the intersection. However, if we wanted to determine an event where A or B are both can occur, so that's everything here. Both circles, if you like, are the circles that are unique, are part of the circle that's unique to both A and B, and also the intersection. Well, that's called a union B. That means that either A or B both occur. Now, you kind of have a situation where there's no intersection. In this case, therefore, the probability of A and B occurring, or A intersection B, is 0. And the terminology for that is that A and B are mutually exclusive and they're a disjoint set. So it's quite important to be familiar with that terminology. The disjoint sets come in quite a bit in problem solving. So really, in relation to set theory, that's it really. The A intersection B, or A and B, where A and B both occur, or this case, A union B, A or B are both occur, and when we have A and B equal to 0, mutually exclusive disjoint sets. Have we got a question there, Eamon?
Apologies, I was muted.
Yeah.
The question is, will we be sent this PowerPoint?
No, not the PowerPoint slides, but there will be a video shared, I think, Eamon, is that correct?
There will be a video of this afterwards, yeah.
No, we don't share the PowerPoint slides, but you'll have it on video. I know it's important to be able to go over it again, and that's good, because there's a lot to take in the tutorial itself. So yes, certainly, by all means, look at the video again. Now, we move on to the axioms of probability, or the laws of probability, whatever you want to call them. But there are not that many of them, but it's important that you remember them, because, as I mentioned, it looks like there isn't a whole lot of information on these in the maths tables, so I stand to be corrected. So maybe, Eamon, if you got a chance just to look at your version of the maths and formula tables, but what I saw the other day, there's not very much around this space. So it's important to have that information when you go into the exam. So the first axiom, we've seen this a number of times, look, that the probability of an event must be less than or equal to 0. Or sorry, must be greater than or equal to 0 and less than or equal to 1. So that's fair enough. We're familiar with that now. The probability then, if we have probability of sample space equal to 1, then that's how that's designated. So it means that, yeah, the probability equals 1. That's and then if we've a probability of the null set of not happening event, so that's how that's designated. That equals 0. Now, I suppose the important ones here in axiom 3 are if you have an event ARRB, probability of ARRB, then that equals the probability of A plus the probability of B if A and B are disjoint sets. So just, sorry. So this is, if we're in this situation here, if they're disjoint sets. So this, you'll see this is going to come up, some of this later here. So, but likewise, if we have a situation where we have three sets here, A, B, and C, then the probability of A or B or C is the probability of A plus the probability of B plus the probability of C if A and B and C are disjoint sets, and so it goes on. So that's just an important axiom to remember. Now, this is very important, the probability of success and failure. And as you see in the question we're going to look at later, sometimes it's easier in a question to determine the probability of failure rather than success. And when you have the actual probability of failure, then you're able to calculate the probability of success from that. So here we have our sample space again, rectangle here we have an event E here. So anything outside of the circle here is designated the complement of E. That is the elements of S that do not belong to E. Now you can see it's this E quote mark, apostrophe, whatever. That's how it's designated here. So you'll have to be familiar with that. And that's the complement of E. So some important points here, that E apostrophe and E are disjoint sets.
Sorry, Ed, there's a
yes.
question came in there
yes.
about what is a disjoint set?
The disjoint set, well, we're looking at one here now. There's no overlap. That's the basic. So if you have the two circles, in this case, there's no overlap here. So we've the circle, and we have the rest of the rectangle, if you like, that isn't the circle. They're disjoint sets. And normally, when we looked at the previous slide with two circles, but there was no overlap. There's no intersection between the two. So that's what disjoint sets are. No overlap. And as I say, in this case here, our disjoint set, okay, we're using circles, but it's a circle and the rectangle with the circle taken out of it, if you like, they're the two disjoint sets in this case. So E, the complement of E apostrophe here, and E are disjoint sets in this case. So the actual sample space then is E E dash, sorry, the dash should be inside there. That's the sample space. So sample space is the combination of E and the complement of E. Therefore, the probability of the sample space is the probability of E and E dashed, and therefore the probability of the sample space is always 1, and that equals the probability of E plus the probability of E dashed, or sorry, E apostrophe. Therefore, working that out, just doing the algebra, the probability of E equals 1 minus the probability of the complement of E. So this is what it's all leading up to here. Therefore, the probability of success is 1 minus the probability of failure, and that's the important point. I know there's a fair bit of working in there and a bit of confusion there with this apostrophe should have been inside here, so apologies for that. But the bottom line here is literally is the probability of success is 1 minus the probability of failure. So again, if it's easier to calculate in a question the probability of failure, and the question is asking what's the probability of success, calculate the probability of failure, and then take that away from 1, and you'll get the probability of success. And we'll see that now in a minute. So this is an example where it is easier to calculate the probability of an event not happening or a probability of failure, whichever way you want to think about it, rather than the event happening. So again, taken from Aidan Rountree's book, Effective Maths 2, a multinational company with operations in France, Italy, and Ireland has a board of directors which consists of 7 French, 6 Italian, and 5 Irish directors. A group of 3 directors is to be chosen at random to attend a conference. What is the probability that there is at least 1 Irish director in the group selected? Now, note that including the term "at least" in the question is a prompt to consider using a success and failure approach. Success is getting 1, 2, or 3 Irish directors in the group. Failure is the probability of getting no Irish directors in the group, which is easier to determine. So you'll see now from the worked example here. So you should be familiar with the steps here. Step 1, calculate the total number of possible outcomes, sample space, using NCR, where n in this case is equal to 7 plus 6 plus 5 equals 18, and we want 3 directors, so that's why R equals 3. So this is n 18 or 3. NCR, working that out, gives us 816, which is our total number of possible outcomes, 816. So that's the first step. So this is where we're going to go for the event not happening, or for failure, if you like. So calculate the outcomes of getting no Irish directors using NCR, with the 3 directors chosen from the 7 French and 6 Italian directors. So in this case, we're going to only have the 16 here in N, and 16. Again, we're going to have 3 directors. Or sorry, 7 and 6 are 13, and we're going to have 3 directors. So the NCR calculation will have N as 13 and R as 3, and that equals 286. So we calculate the probability of that event of having no Irish directors. So that again is the 286 over our total number of possible outcomes, the 816. Simplifies to 143 over 408. And then it's quite an easy step then to calculate the probability of success, which is 1 minus the probability of the failure. So the probability of getting no Irish directors is 143 over 408. So we take that away from 1 and we end up with 265 over 408. So very nice example, I think, they're showing how it's sometimes better to calculate the probability failure rather than success, and then work out the probability of success from that. So important concept there. Anyway, the thing is the probability of success is 1 minus the probability of failure. So now we'll come on to some rules of probability. And again, just some terminology here, designation, just important to be familiar with. So in this case, A / B means A, not B. So it's this part of the circle here. Anything that's A but doesn't overlap with B. So we know our intersection here, A and B. That's that part there, shaded yellow. And B, not A, is again any part of B that doesn't include A. Now, they're all disjoint, mutually exclusive, because they don't overlap one another. So that's important then. So we can write it in this way. So if we designate A not B as X, A and B as Y, and B not A as Z, we can write then the total here of A union B, if you like, or A or B, is equal to this portion X plus Y plus Z. So grouping things together here, we can take the X with the Y here. We can add Y to Z and take away a Y, if you like, to maintain the equation. And we end up with X plus Y, X and Y, which is A, and Y plus Z, which is B, and then minus Y, which is the intersection, the A and the B. So it's just a neat way of showing that the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. And then just coming back to our disjoint sets, if you can imagine those circles being taken apart and having no intersection here. Well, in that case, the probability of A and B is 0 because there is no intersection. So we're just left with, for disjoint sets, the probability of A or B is equal to the probability of A and the probability of B. Very important, this concept, this general rule, and we'll see it being used later.
Sorry, Ed, I've got a question that came in there.
Yes.
Why isn't its sample space 816 minus probability no Irish directors 286? I don't understand why you divide. Why isn't it sample space?
This going back to this.
Yeah.
Yeah. So yes, the sample space here is 816, yeah. And the probability of the failure, the probability of just getting no Irish directors is 286. Okay.
So the question is, I don't understand why you divide.
Because that's that's how probability is determined. You first of all calculate the sample space. So that's the total number. So let's say if to take it simply, let's say, you know, we often hear there's 1 in 100 chance of something happening. Well, what you do is there's you know, or 1 in 100 things can happen. An event can happen. So the total number of possible outcomes is 100. And the chance of that a particular one happening is 1. So that's how you determine the probability is 1 divided by 100.
Yeah, that makes total sense.
You know, so really it's the steps here, they're all the same. First of all, the sample space is all the possible outcomes, you know. How many days in the week, you know, the possible outcomes are going to be 7 days in the week, 365 days in the year, you know. And then the number of, if you were to think of it this way, so, you know, how many Saturdays, the probability of the you know, Saturday in a week, it's only 1 Saturday, but there's, you know, 7, the probability of a day in a week being a Saturday, there's 7 days, but there's only 1 Saturday, so it's 1/7. So if you think of it that way, then I think it can help. But certainly the first step is always, you know, getting an idea of the total sample space. Then the number of the outcomes. In this case, getting no Irish directors, and then dividing that outcome, that event, the probability of that event by the total number of possible outcomes. Okay. So important to go over this again. If you don't totally understand it, I'd advise doing that, because it is used in questions, and we'll be looking at one now in a little while. But it's it brings in quite a bit just in terms of the understanding of different probabilities, a probability of A and B, or A or B, and so on. So, and the disjoint sets as well, which is very important. Now, it's a bit complex here, and I haven't seen questions with conditional probability in them. So I won't spend too much time on this, but it's just important to understand it. And really, it's the very last line here on the slide that's important. Independent events. This rule is used to determine the probability, or to be able to write the probability of A and B for independent events in this way. And again, that comes up in the question, in the solution to the question we were looking at. But just to understand how it's designated, that's the probability of B being conditional on A. So this is what the bar means here, the vertical bar, not the backslash. That equals probability of A and B divided by the probability of A. So this is where the conditionality comes in. If each outcome is equally likely, then the probability of B dependent on A is equal to, again, it's the same really, the A and B over A. If A and B are independent events, then the probability of B dependent on A is just equals probability of B, and the probability of A dependent on B is equals probability of A. So just repeating this here, but the general multiplication rule is just multiplying across here by probability of A, just to get the probability of A and B equals the probability of A multiplied by the probability of B, which is dependent on A. That's the general multiplication rule. However, if they're independent events, then we don't need to worry about the conditionality. And we can simplify it to this. The probability of A and B equals the probability of A multiplied by the probability of B for independent events. Now, as I say, normally you'd be quite unlucky if they're going to go into this, having to use the general multiplication rule. So normally it would be this, you'd be talking about independent events here, which is a lot simpler. But you need to remember this this rule, which, as I say, will be used in problem solving. So we'll have a look now at a question here. I'm just going to share another screen in order to do this. This is a fairly recent question, again from 2019, paper 2, question 6. So we're going to look at, this is part A of the question. And it's a good question because it covers quite a bit what we've been looking at over the last number of slides. It's a fair question, I think, but there's a little bit of working out in it, more than I think you would normally have with these questions. But anyway, we'll work away on it. So, as always, very important to read the question, underline keywords, spend your time with it, and then move into solving the question and working through the steps. So these are two independent events. So, you know, remembering back to the rule we looked at, this is good news here. They're independent events, so there's no dependency. So that's good. It's going to be a simpler problem. So they're independent events, F and S. They're represented by the Venn diagram. So you should be familiar with these diagrams now after what we've been looking at. And you should be familiar with the designation here, that the probability of F backslash S. So it's not dependent. It means that the probability of F, but not S, is equal to a quarter. The probability of F and S, so the intersection, is always the intersection here, is equal to a fifth. And the probability of S not F equals X. And the probability of F or S, the complement of F or S. So F or S would be everything here in the two circles and the intersection. The complement of that is anything outside of those two circles, including their intersection. So this is the apostrophe here, the complement, so equals Y. So that's why it's so important to be familiar with how these terms are written before going into the Leaving Cert. And so anyway, we've gone through the question in detail here, and we'll start working away on it. So what I like to do to start off, even though it's some of the detail is written in the question, I like to rewrite it so you have all your key information written down first. Now, just to be clear, what we're talking about here, the quarter is that, okay? So probability of F, but not S, not the overlap or the intersection. So that's a quarter. So next step here, the probability of F and S, that's straightforward. That equals fifth. So that's what we're talking about here, just to be clear. And then the probability of S not F equals X. That's what we're trying to find out. So in that case, it's this here. Okay, so hopefully everyone is happy with that. So the first thing we'll do is we'll calculate the probability of F itself. And that's quite straightforward because the probability of F is the probability of F not S plus the probability of F and S. So it's a quarter and a fifth. So we can see that from the Venn diagrams, the full circle F, if you like. And that equals 9/20. Okay, so that's the first step. Now, from our work that we've done previously, we know from this rule, they're independent events now. Very important to get that they're independent events. So we know for independent events from our rule, the probability of F and S equals the probability of F multiplied by the probability of S. So in fact, that's the key part in this question here. Now we've already calculated the probability of F. And we know that the probability of F and S is a fifth. So we can write fifth equals probability of F is 9/20 multiplied by the probability of S. Okay. So that implies the probability of S equals 20/45. But the probability of S is also equal to X plus a fifth. So it's the full circle, if you like, the full circle S here. And that equals, in turn equals, what we've just found out is 20/45. So bit of algebra here, X equals 20/45 minus 1/5, which equals 11/45. So that's the first part of our question done. So they said here, find the value of X x and y doesn't equal to 0, so that's good. So we found here that the value of x is 11/45. Now, so second part of the question then. So we want to find the complement y here. So and that's the complement of f or s, f union s, if you like, the complement of those, the combined two circles there. So we can write this way. We know that we can use what we found already out, having found x. We know that f union s, if you like, for s is a quarter plus a fifth plus x, which is 11/45. And you can do the workings yourself if you like, but that comes out to 625/900. Okay. But we know that y equals the probability of f union s apostrophe is the complement there. But we also know from previous rules we would have worked on, remember the success and failure rule we came across. We know that that equals 1 minus probability of f or s. So it shows how important that rule is. So therefore, because we've calculated the probability of f or s here has been 625/900, it's straightforward to calculate y by saying y equals 1 minus 625/900, which is equal to 275/900, which simplifies to 11/36. So question done there now. Quite a bit in doing that, but I think fair enough question. But the key here to solving the question really was this here, the probability of f or s being the probability of f multiplied by the probability of s, and then this part here where the probability of failure is 1 minus the probability of success. The rest of it really was just a matter of working through the Venn diagram, doing the calculations, but a nice little problem, and I think it summarizes a lot of what we've been looking at in the tutorial, certainly the second half of the tutorial. I'll just go back here. So can you see my screen again, Eamon?
Yeah, I can see it
on the PowerPoint. Yeah.
PowerPoint, yeah.
Thanks. Well, that's all I have for you this morning. I hope you've got something from it. There's quite a bit to take in, but if you're unsure of any of the points, you can look at the video. Just before finishing up there, just to summarize some additional resources, I've spoken a number of times about Effective Maths too by Aidan Rowntree. If any of you have that or know anybody who has it, there's some very good information on probability in that and some good examples. I like this book, Solving Mathematical Problems, Personal Perspective by Terence Howe. If you're really interested in getting into problem solving techniques, that's a very good book. A little heavy at times, but it's a good resource. Then, as always, there's so much out there on the net. So, Khan Academy is very good, very good for mathematics, physics, and so on, science topics. So they have a good video there on statistics and probability. I like this this website here, decode.fr. It's a French website, but it'll generate the permutations, combinations for you. It just helps with your understanding of permutations, combinations. You can put in different data and it will generate out the permutations. Good to see it on the screen. If you're just a bit unsure about the Venn diagrams and the sets and so on, so set theory, there's a good reference there to a video on Venn diagrams. I found it quite good. And as always, please go to examinations.ie for links to past exam papers, marking schemes, and so on. So there'll be other examples of probability questions there that you can try. Please give it a try first before jumping into looking at the solution. So I wish you all the best with your studies, and thank you again for attending this morning, for all the challenging questions. Sorry I hadn't maybe a great answer to the conditional one, but I'll be looking it up now to get to have one. But I hope you've got some good information from this tutorial. Bye now.
So all that's left for me to say thank you, Ed. It was a great presentation, lots of examples. And to the students, hopefully you got something out of it, and hopefully also we see you next week for the sequences and series tutorial. Bye for now.